So, hey folks, how's everybody?
Good.
Good to hear from you, Edwin. Good to see you. Hi, Kendall. Hi, Danny. I want to congratulate you all for doing so well on test two. And if you didn't make the grade that you were hoping for, do not be discouraged. Okay, we still have another test, and we have the final exam. So, believe it or not, this class is easier to pass than you think. So. Um, but some of you did very well. Listen, while I've got your attention, isn't it Danny and Kendall and Nick? Nick, are you there?
Yep, turning my camera on now.
Okay. You're my three tune students that are left, I think. So what we need to do is we need to decide on a day for the final exam, and I'm finally going to get to breathe the same air with you because we will be at Tune. I'll be driving up to give you the final exam. And I'm wondering whether Friday or Monday is a better day for you all. So it's the week of exams. So think about that. And I will send the three of you an email and we will discuss and decide a definite time and day for the final exam. Okay. For the folks at TU, we have that final exam on Saturday afternoon. But I understand I can't ask you all to drive to TU for the final. So I'll come and meet you. So be thinking about what day would be best for you, Friday or Monday, on either side of the Saturday, okay? All right, great. Okay, so let's get started. You'll see me looking over because I'm down to one screen here while I'm still working on getting adapters for my new PC, but it's okay. I can see you right here. So here's our do now problem. I've already posted web assign and special homework 9, and there are a couple of problems not just exactly like this, but similar to this. If you look at our notes from last time, or time before last, we had a problem where we had to factor out a particular value before we could apply the formula. The thing to understand about this hint, and I'm going to just post an extra page of what I'll call just extra notes, is that when we sum up a bunch of numbers, whatever the terms are, um, from 1 to n, we could split that anywhere. Okay, so in particular, if we're adding 1 plus 2 plus 3 plus keep on going up to plus n, somewhere in there's a j, and then there's the next integer, which is a j plus 1, right? So we could just split this sum up to 1 plus 2 plus keep going up to plus j plus, and then pick up at j plus 1, and then plus j plus 2, plus dot, 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 plus n. Where we could group these together like this if we wanted to. Do you see that we can split a sum up into two sums? So in this do now, we're looking for something like this because our sum that we're looking for doesn't start at 1. It starts at 621. So our j plus 1 is 621, you see. So when we start to work this, we're going to realize, okay, we can take the sum from 1 to 1,000, but subtract from that sum from 1 to 6,000. From 1 to 6,000, we can subtract from it the sum from 1 to 620. And that'll leave behind, right? So if we just take the whole sum from 1 to 6,000 and subtract this part to that side, then it leaves us the 621 plus 622 plus all the way up to 6,000. See what I mean? Let's go ahead and solve this now. So today we're going to be in sections 5.2 and 5.3, and after we finish this sum problem, we'll go right into mathematical induction problems. But when we try to solve this, folks, All we got to do is just realize, hey, the sum from I equals 1 to 6,000 of I is equal, excuse me, not 1, 621. The sum from 621 to 6,000 is take the whole sum from I equals 1 to 6,000 of I and then subtract the first 620 of those. Now, it's a big sum minus, the smaller sum. And if we use the formula, here's our formula. The sum from I equals 1 to 6,000, of course, n is 6,000, and c, it starts at 1, so we can actually play the game. So it's 6,000 times 6,000 plus 1 over 2 minus, and now we play the game with n equal to 620. And so it's 620 times 621 divided by 2. And I think this turns out to be something like 18,003,000 minus what 192,510. You can check me on that. I think it turns out I'm really not that interested in this part. I figure if you can get this part, you can surely use your calculator to get the answer. It's like 17 million and change. Do you have any questions on that? Do you see why we do this subtraction? First, we're trying to get rid of 1 plus 2 plus 3 plus dot 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 plus 620. We're trying to get rid of this from the whole sum that would start at 1 and go all the way to 6,000. So we do that by subtracting away the sum from I equals 1 to 620. Questions? Hey, listen, let me explain something kind of important to you. This is the only expression where all we're going to see is the indexing variable, because literally the value is the indexing number, right? We're just plugging in the indexing number I equals 621 plus, and then the next one, 622 plus, and then the next I, 623. See what I mean? We will never see another formula that only has I sitting here. It's always going to be something more involved than I. Okay, so I just don't want you to make the mistake of thinking that we're usually going to have just an I here. Okay. Well, I'm going to give you, this was a do later problem. How many, I'm just to raise the hands or just pipe in. Hey, Eric. Hey, Ronnie. Glad to see that you're here. Let's see who else has gotten into the room. Oh, that's it. Um, just curious. You're not in trouble or anything, obviously. Did anybody actually work the do later that was this problem? Okay, that's fair enough. All right, so why am I even asking that? The reason I'm asking that is when I give you a do later, you might want to actually do it later. You might want to go ahead and just take the time and do it because it'll help you later, that kind of practice. Let me give you a do later now and another hint. And maybe you really will do this one later. By the way, the special homework 9 is posted, and if anybody wants to come into office hours tonight, we can discuss it. It's not due until next Wednesday. I also sent an announcement about our WebAssign schedule. We had gotten a little bit off schedule because I gave a little bit more time for WebAssign right before test 2, but we're back to our normal schedule Sundays and Thursdays. So the next WebAssign, which is on mathematical induction, is due Sunday night. So calculate this sum using our formula. But this is going to look a little different. This is similar to, like I said, an example that we had seen before. And here's the hint. I'll give you the hint right off the bat. If we have a multiplier, k, times the sum 1 plus 2 plus 3 plus dot, 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 plus n. If there's some common factor that we could pull out of all of the terms and, call it k, then the sum is just k times the sum that we usually use, which is n plus 1 times n, or n times n plus 1. Of course, multiplication doesn't care which factor comes first, over 2. In other words, if you have a k written outside the sum from I equals 1 to n of I, you can just take that multiplier k and use it as a multiplier outside of our formula for the sum from I equals 1 to n of I, okay? So here's the actual sum I'd like you to work on. 1,000 plus 1,002 plus 1,004 plus 1,006 plus dot, 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 plus 10,000. And so there's a reason I'm giving you this hint. You see, these terms don't increment by plus 1, do they? The difference between the terms is bigger than 1. So there is going to be something you'll be able to factor out of all of these. So this hint is going to be in play. But the hint that we used tonight for 621 plus 622 plus dot, 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 plus 6,000 also will come into play, because this doesn't start at 1 either. It's not like you can pull 1,000 out of each of these, okay? So it puts together both of those hints to make what I hope you will find an interesting and challenging little arithmetic problem. Okay, so we are going to talk about induction tonight. And what we're going to do before we start our proofs is we're just going to remember the work that we have to do when we're writing a proof by mathematical induction. So let's recall the work we must do to write a proof by mathematical induction. Oh my gosh, it's all caps. I'm not yelling. That, well, what do we prove? We prove some statement, say P of n, concerning an integer n, is true for all integers n greater than or equal to some lowest level step where we want to stand at first. Call it n naught. So let's recall the work. Well, we have to prove this predicate statement holds at n naught. So we have to prove P at n naught is true. Remember, that's called our basis step. That's the first thing that we do. Once we do that, we're standing on the bottom step of our stairway to mathematical heaven. Then we have to write the induction step. Let's remember what that looks like. We let k greater than or equal to n naught be an integer. So we just let our reader know, hey, we're going to introduce a new variable k, and it represents any integer that's bigger than or equal to n naught. Assume P of k is true. So folks, this is called our inductive hypothesis, or our induction hypothesis. It's what we get to assume, because remember what we're trying to do. We're going to try to stand on the step K and then prove that we can step up to the next step. So that's what we do in this induction step. Then we'll prove that P evaluated at K plus 1 is true. So this is where we prove the if-then. If P of K is true, then P of K plus 1 is true. Okay, remember? And then finally, the last thing we do to finish our proof is to invoke the PMI, the principle of mathematical induction. We are not proving the PMI. It's a principle. We get to use it. When do we get to use it? We get to use it when we have established its hypothesis. And its hypothesis was a two-part hypothesis. The first part of the hypothesis of the principle of mathematical induction is that the statement is true at some low-level value in naught. The second part of the hypothesis of the principle says, if P of K is true, then P of K plus 1 is true. Once we've established these two statements, we have satisfied the hypothesis of the principle, and we simply get to apply the principle. We invoke the PMI, the principle of mathematical induction, and simply state, that P of n is true for all integers n greater than or equal to n naught. Because that's what we're trying to do. We're trying to show that the statement is true no matter how large n gets. Now, one of the fascinating things I think about the principle of mathematical induction is it allows us to prove an infinite number of statements with one argument. Think about it. With a finite number of symbols, we express an argument that proves an infinite number of statements because n is unbounded above. So we're proving that this P of n is true no matter how large n gets. And you can think of that as an infinite number of statements, one for each value n as n grows, starting with n naught. So I do think it's sort of amazing. So let's get some more practice, some practical hands-on practice, proving some statements using the principle of mathematical induction. We are going to review some of the most important things that we need to know about making arguments concerning equations. And one of the main things that we discussed last time that we will continue to discuss is that we may not begin with the statement we wish to prove. So if we're trying to establish that something equals something, we cannot start our argument with that equation. We have to be smarter than that. All right, here we go. Example 3. Prove the following is true for all integers n greater than or equal to 1. The statement is 2 plus 4 plus 6 plus ... plus 2n is equal to n squared plus n. In other words, we're looking at the sum of the first n positive even integers. These are all the evens. You know, when you think about this relative to the statement we proved last time that 1 plus 2 plus 3 plus ... plus n is equal to this expression divided by 2, it makes sense that if we double 1 to get 2 and double 2 to get 4 and double 3 to get 6 and double n to get 2n, that we would double the expression on the right side, and instead of getting n times n plus 1 over 2, we get n times n plus 1. That's what n squared plus n actually is. It's n times n plus 1, of course. All right, here's our proof by mathematical induction. I apologize for not having space between the start of the proof and the statement. All right, so we're going to just write the expression. On homework, folks, definitely write the statement P of n as the first part of your proof. On the test, you can just say, see the statement above, I'll show you that. But on the homework, you want the P of n on your piece of paper right in front of you. Trust me on that, because otherwise it's really easy to make a clerical error if you keep looking back and forth at the screen instead of having the statement P of n on your paper. So I'm going to model what I'm talking about here. Let's just write the statement. And I'm going to use summation notation. The sum from I equals 1 to n of 2i, right? These are the evens, is equal to n squared plus n. So here we're using summation notation. And there's a reason why we want to use summation notation, because we've learned some skills. I also want to remind you that this side is what we call the left-hand side of the equation, or LHS, and this side is what we call the right-hand side, or RHS, okay? Remember, we can't start with setting these two equal to each other at any stage of the game, but there are a couple of strategies that we do have. One strategy is to look at the left-hand side and evaluate it, figure out what it evaluates to, set that aside. Then look at the right-hand side and evaluate it, figure out what it comes out to, and then compare those two evaluations and make sure that these two evaluate to the same thing. Then we get to say that these two sides are equal. The other strategy, which we use in the induction step, is to start with the left-hand side and work on it using algebra and things we've learned about summation formulas, and then our inductive hypothesis, and then more algebra to turn it into the right-hand side. But we will never start our argument by saying these two are equal to each other. All right, let's write our basis. Here we go. Skip a space and get down to the basis. Okay, so the first sentence in the basis step is always the same. We have to tell the reader what n naught is equal to. Let n naught equal. And look what n naught is equal to. We're told n naught, always. We're told where to start the proof off. So this is n naught. So we tell the reader, hey, let's let n naught equal 1. What do we wish? The wish is always the same. In the basis step, we wish to show that P evaluated at n naught here, that happens to be 1, is true. So that makes it easy. It's kind of like formulaic. Introduce n naught. Our wish is to show that the predicate statement evaluated at that value n naught is true. Now we're going to look at the left-hand side of P of 1 and figure out what it evaluates to. So the left-hand side of, of P of 1 is, okay, here we go. All right, so let's just remember how we deal with it. You see, in P of n, the argument is n, but in P of 1, the argument is 1. So we just replace n with 1 everywhere we see the n. So there's just an n up here. So we're just replacing the upper limit of the sum with 1 instead of the n. So we're looking at the sum from I equals 1 to 1 of 2i. Well, that's just a single term. It's just the term when I is 1. So this is 2 times 1, which of course is 2. So the left-hand side of P of 1 is 2. Now we're going to look at the right-hand side of P of 1. The right-hand side of P of 1 is, well, we're just going to plug in a 1 everywhere we see an n. So that's going to be 1 squared plus 1, which of course is also 2. Yay, that's what we needed. So So the left-hand side is equal to the right-hand side. It's fine with me if you just use this simple notation. And that means P of 1 is true. So we are standing on the bottom step of our staircase to mathematical heaven. Any questions? All right. So now our next job is to show that if we're standing on the step K, that we can step up and stand on step K plus 1. This is called the induction step. Please always skip a line and indicate where your induction step starts. So now the induction step always starts the same. It's kind of like the basis step always starts with you saying, let n naught equal whatever it is. We wish to show P evaluated at that n naught is true. Induction step, just say this. Let K, I'm going to put it in red because K is now going to be our argument, greater than or equal to n naught, which was 1, be an integer. So basically, you're just telling the reader, hey, we've got a new variable. We're calling it K. This is its range. It starts at the bottom level and is bigger than or equal to that, and it is an integer. And now here's our induction hypothesis. Assume P of K is true, i.e., assume, and now we're going to actually write P of K. All right, well, what the heck is P of K? Well, if this is P of N up here, P of K, the argument is K, right? So we're going to put a K everywhere that we see the N. And this is the one time we can write the equation because we're assuming that it's true. We do get to assume that the equation is true when N is K. So it's the sum from I equals 1 to K of 2I. That's not 2 to the I, folks. It's 2 multiplied times I, of course, equals, and then instead of N squared, it's K squared plus K. Okay, so this is our inductive hypothesis. And I am going to put my green box around that because this is my visual. Now, this is our money in the bank. This is our inductive hypothesis. We have to have this. We're going to use it, obviously. Now let's write our wish. And because we can see P of K, I can scooch this up because now you see P of K and we'll be able to figure out what P of K plus 1 is. That's what we wish. The wish is always the same. In the inductive step, we wish to show P of K plus 1 is true. It's always the same wish. We wish to show P of K plus 1 is true, i.e., we wish to show, and now let's write P of K plus 1. Ah, can everybody take a minute and write P of K plus 1? See if you can write P of K plus 1. Everywhere that you see a K, it's going to get replaced with K plus 1 because the argument is now K plus 1. So take a minute and then we'll compare notes. You do need parentheses because we are replacing a monomial K with a binomial K plus 1. Did everybody get this? This is the one disadvantage of not being in the same room together. Normally I would wander around and peek over your shoulder, right? All right, so listen, folks, this is my little visual to help me Just remember, hey, this is a dreamy, cloudy wish. This is a wish. Okay. This we have in our hand. This is the proof money we get to spend. This is our wish. All right. So our strategy is going to be to start with the left-hand side of P of k plus 1 and use algebra and the inductive hypothesis until it looks like the right-hand side. Okay, that's our strategy. Those strategy notes are actually in the notes that are posted, so I'm not going to write that here. I just said it, so it's also, like I said, it's in the written notes, but that is usually our strategy if what we're proving is an equation about a sum or a product. We start with the left-hand side and we work on it until it looks like the right-hand side. So do tell your reader what you're doing. Let's just tell the reader, hey, starting with the left-hand side of P of k plus 1, we have, well, what do we have? Well, we have this, right? This is the left-hand side. So we have the sum from I equals 1 to k plus 1 of 2i. Now, we're going to use what we practiced last time. We're going to practice breaking off the last term. We know that we can write this as the sum from I equals 1 to k of 2i plus the sum from I equals k plus 1 to k plus 1 of 2i. Remember, this is called breaking off that last term. And there was a reason why we practiced doing that last time. Why would we do this? What is the efficacy here? What in the world is this going to help us with?
Because we can like substitute the one with I equals 1 of k with k squared plus k.
Exactly. Yes, Ronnie, to use algebra and swap the portions of the equation. But you're both exactly right. We want to use this induction hypothesis, but we can't do it with k plus 1. We can only do it if the upper limit is k. And now we have that. So just to kind of visually remind you, when you're looking at the notes, that this is what we're going to substitute into. I'll put the green box around that. And now let's make the induction substitution. This is equal to k squared plus k. I'll suppress the red now. This is k squared plus k. And I'll write this sum like this. I equals k plus 1 to k plus 1 of 2i. But in a minute, we're going to just evaluate this. But the reason I'm not doing both at the same time is because I don't want you to be confused about what's actually the induction step. The induction step is from here to here, this substitution. And you have to tell your reader, you must do, or you'll lose a point or two when you use the induction hypothesis. So you can either say by the inductive hypothesis, which we did last time, or you can say by induction. It's a little shorter and it means the same thing. It means we're using the induction hypothesis to make the substitution. Now, let's just take a look. Oh, we started with this, and now we've got this. We're trying to get the right-hand side, which looks like this. So we're closer than we were, but we still have to get rid of this summation symbol, right? So let's go ahead now and evaluate this term. Well, this is the single term where I has the value k plus 1. We do have to use parentheses because, again, k plus 1 is a binomial. So now let's take stock. And this is the way you're going to play this game when you're working on these. You're going to want to keep looking at where you're at and comparing it to what you wish to get. You see how important the wish is now? This was the origin of the wish in my teaching career, was exactly this kind of proof. Because, man, if we don't know what we're trying to get, how in the world would we get there? But see, we've got our eyes on exactly the expression we're trying to turn this into. So this is one of the times that we're going to have to actually distribute. We'll distribute the 2 across this k and get plus 2k plus 2 so that we can have what we need to have k plus 1 quantity squared. Well, everyone here should know that k plus 1 quantity squared is k squared plus 2k plus 1. If you need help with that, you should come to office hours and we can work on squaring binomials. So we need k squared plus 2k, so we have 2k here. But we only need plus 1 of this, so we can split this up to plus 1, and then this k is here, and then the other plus 1, and that is the same as this. But the reason I've done that, you can see, because now we can write k squared plus 2k plus 1 as the quantity k plus 1 squared, which it is, plus the leftovers, which is exactly what we needed left over, plus k plus 1. And now we can say which is the right-hand side of p of k plus 1. So we started with the left-hand side, and we worked by breaking off the last term, using our inductive hypothesis, evaluating that last term, doing some algebra, keeping our eye on the prize until it turned into the prize, which is the right-hand side. So we are almost done with our proof. We just can say, hey, so p of k plus 1 is true, because that's what we just showed. And now we will invoke the PMI, invoke the principle of mathematical induction. Thus, by the PMI, you don't have to write out principle of mathematical induction. You can just say PMI. We can now say that the sum from I equals 1 to n of 2i is equal to n squared plus n is true for all integers, or holds. You could also say holds. I think in the notes it says holds for all integers. N greater than or equal to, what was our n naught in this one? We got to put the n naught there. Do you remember what we started off at? 1. Right. So we've just proven that it's true no matter how big n gets. Questions? Answers? Meaning of life? Anybody got that answer for me? Thanks, Ronnie. Yeah, I've opened my chat now so I can see your comments. Good. Yeah, 1 was our n naught. Good, thank you. All right, let's do another one. Practice makes perfect. We've got a couple more we're going to do tonight, but let's switch gears. Everything we've been doing so far, we've done 2 proofs by mathematical induction, have been with summation formulas. Thanks, Ronnie. Hello. So let's prove the following, because let's do something a little different. Let's play with the product. Is true for all integers n greater than or equal to 2. Greater than or equal to 2. So right away, we know what our n naught is, folks. N naught is going to be 2. And when we're asked to start with 2 as n naught, I guarantee you the reason that we're asked that is because it's not true for 1. We'll take a look at this and we'll see. So it's the product from I equals 2 to n of the expression 1 minus 1 over I. The claim is that that product is equal to 1 over n. So here's our extra notes page. Let's just look at this for a second. Let's look at this, what this is actually saying. Okay, so what is the product from I equals 2 to n of 1 minus 1 over I? And why would it turn out to be this? This is a kind of cool one because it turns out to be what's called a telescoping product. Let's see what this is equal to. All right, when I is 2, then it's 1 minus a half. Do you agree? Of course. When I is 2, we just plug in a 2. But it's times, all right, now then we increment I to 3. And so the next factor is 1 minus 1/3 times, right? And then the next factor is I goes up from 3 to 4. So it's 1 minus a fourth times, keep on going, dot, 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 times. And then, of course, the last value is 1 minus 1 over n. Now, what is that? Okay, well, let's think about it. What's 1 minus a half, everybody?
1/2.
It's a 1/2. What's 1 minus a third?
2/3.
Yep. 1 minus a fourth?
3/4.
Yep. Times, dot, 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 times. And 1 minus 1 over n, well, it's n minus 1 over n. The top number is always one less than the bottom number, if you notice. You can also just get a common denominator n, right? We have to multiply 1 times n, and you've already got the negative 1 over n. So that's another way to get n minus 1 over n. Well, check out what happens. This is a product, everybody. So listen, this 2 cancels with this 2. That's what I mean by a telescoping product. You know, you can kind of take a telescope and squish it back together and make it short. Like what? So the 3 would cancel with the 3 up top. This 4, well, there would be a 4/5 here, right? Would cancel there. And then the one right before, the factor right before, what we would call the penultimate factor would be like n minus 2 divided by n minus 1. So this n minus 1 would cancel with the n minus 1 down there. And look what's left. On the top, the only thing that's left is the 1. And on the bottom, what's left is the n. So, I mean, that's why this is true. It's easy to see that this is true. But we're going to prove it by mathematical induction. Okay, here we go. Proof by mathematical induction or by mission impossible. Okay, let P of n be the statement above. Again, on a test, when you've got it right in front of you, it's fine to just save time and say, let P of n be the statement above. But on homework, go ahead and write, let P of n be the statement below, and then go ahead and write P of n so you have it on your paper. Okay, I don't need to say that again. All right, our basis. What's the first statement that we make in our basis step? We let n
Let
naught,
n, oh,
good.
let n not be 2.
Yeah, let's let n naught equal 2 because that's where we're asked to start. And what do we wish to show? That P of 2 is true. It's always going to be the same start. So again, same game. We can't set it equal to each other without doing it separately. So the left-hand side, the LHS of P of 2 is, well, let's see. It's the product from I equals 2 to 2. So it's just that single term where I is 2 of 1 minus 1 over I, which of course is 1 minus a half. We already looked at that. And it is, of course, 1/2. So the left-hand side of P of 2 is 1/2. Let's hope for the best, that the right-hand side is also 1/2. Here we go. The right-hand side, and if you don't get the same value when you do the left-hand side and the right-hand side, you've got an algebra error or a typo. You might have written the problem down wrong. This should always work out. The right-hand side of P of 2 is just, well, it's just 1/2, which is, of course, 1/2. So the left-hand side equals the right-hand side, and P of 2 holds. Easy peasy. All right, let's write our induction step, or our inductive step. Tell your reader what K is. Let K greater than or equal to, well, the bottom level is 2, be an integer. Just state the K is an integer and give the range. And then induction hypothesis, right? Can everybody write the inductive hypothesis? See if you can do that now. This is what we assume. Assume P of K is true. I.e., all right, what is P of K? Well, we just look at P of N and we put a K everywhere we see an N. So it's what? The product from I equals 2 to K of 1 minus 1 over I. And that's equal to 1 over. Everybody write that? Everybody get that? This is our induction hypothesis. Here's our proof money. This is what we're going to spend. All right. Now, let's write our wish. What do we wish to show? It's always the same wish in the induction step. We wish to show P of K plus 1 is true. Go ahead and write exactly what that means. You want to write it out. What do we wish to show? It's the product from I equals 2. Everybody get that? So this is our wish. It's just so easy to confuse what we're trying to prove with what we wish to prove. That's why I use this little visual aid. All right, same game plan, folks. We're going to start with the left-hand side and work on it. Use the induction hypothesis. Turn it into the right-hand side. See if you can do it. This is just an algebra problem. Tell your reader what you're doing. Starting with the left-hand side of P of K plus 1, we have, okay, what do we have? We've got the product from I equals 2 to K plus 1 of 1 minus 1 over I. So now what?
Split it into 2 to K, and then k plus 1 to k plus 1.
That's right, and it's a product, so we're not going to be adding them, folks. We're going to be multiplying in between. Good. So I equals 2 to k of this expression, 1 minus 1 over I, times the product from I equals k plus 1 to k plus 1. Just break off that last k plus first term. 1 minus 1 over I. Don't forget to put your expression for your a sub k here, your a sub I, actually. Don't forget to put your a sub I there. That's one mistake that students tend to make is you get so excited about, breaking it together, and that's nice, but then you forget to put the actual expression for the term there. So, and of course now, this factor is the factor we know something about. We know what it's equal to. It's equal to 1 over k, right? So we make that substitution by induction right now. Let your reader know that you're using the induction hypothesis by saying by induction. And of course, this becomes 1 over k. Times this product from I equals k plus 1 to k plus 1 of 1 minus 1 over I. All right, so this next step is the algebra step. Just keep our eye on the prize up there. This is what we're shooting for. So we're going to have to evaluate this term. It's not, we just got to be careful, right? Well, it's 1 minus 1 over k plus 1, right? Because I is k plus 1. So we can compare what we've got with what we're looking to get. And we're kind of a ways off there. But we sure know how to get a common denominator, right? So let's do that, because that'll clean that up and make it a fraction, and we can multiply the two fractions together. Common denominator, of course, is k plus 1. Now the minus 1 is already over k plus 1, so we can just write it down. But 1 has to be multiplied times k plus 1 so that we can put it over k plus 1. Well, that's just k plus 1. And now, of course, we've got 1 over k times, well, what's k plus 1 minus 1, folks?
K.
Yeah. And then on the bottom, we've got the k plus 1. And look what we see. We see that very last telescoping situation happen right here in the induction step, don't we? Which is the right-hand side of p of k plus 1. So it's like magic. So p of k plus 1 holds. And now we invoke the PMI to make sure that we have really completed the proof, because unless we use the PMI, we're not proving that it's true forever after. So by the PMI, we can now say that the product from I equals 2 to n of 1 minus 1 over I is equal to 1 over n is true for all integers n greater than or equal to 2. Questions? So we proved last time, day 18, our formula that we've been using for these games, that 1 plus 2 plus 3 plus dot 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 plus n, right? We proved that formula. There are numerous very useful formulas like that one. I'd like to show you a list of the 3 most useful formulas, especially if you're doing Riemann sums and trying to figure out the areas of the thin, skinny rectangles that fit under a curve. I'd just like to show you these useful formulas, and all can be proven. by mathematical induction. Okay, so the first formula, I'll just call it Roman numeral 1, is the one that we've looked at. 1 plus 2 plus 3 plus dot, 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 plus n. Sum of the first n positive integers is equal to n times n plus 1 over 2. All right, now I'm going to leave, some lines here. 1, 2, 3, 4 lines. And what I'd like you to do later is write this using summation notation. You can do that later. It'll be good practice. Okay, so I'll leave you some room there. In the notes, it's already there, so you can check after you do it. Now, the next formula, well, this is the sum of the first n the first n positive integers, but what about the sum of the first n positive perfect squares? I mean, we could include 0 squared, but it wouldn't add anything to the sum. There's a formula for that. 1 squared plus 2 squared plus 3 squared, and it goes like this. It's also a fraction. It's n times n plus 1 times the quantity 2n plus 1, whole thing over 6. So 1, 2, 3, 4. I'm going to save some room and let you write that later. Use a summation. Let's go ahead and practice summation notation again. What do you think the third formula is going to be?
Cube.
Yes, the sum of the first n perfect cubes. So 1 cubed plus 2 cubed plus 3 cubed plus dot, dot, dot plus n cubed. Now, this is what's really interesting. See the formula for the sum from 1 to n? Well, that is part of the formula for the sum of the first n perfect cubes. It's n times n plus 1 over 2. But there's an exponent that goes here. Now, using natural intuition, what do you think the exponent is? Well, that's 1 cubed. This is 2, this is 2 cubed. This is 3, this is 3 cubed. So your natural intuition, at least my natural intuition, is that that would be a cube here, but it's not. It's really fascinating to me. It's squared. And that fascinated me so much. I spent like a whole year and wrote a paper about why that's true with pictures and everything to show the geometry of it. I'll post the paper on the Blackboard website. I'll have to dig it out and post it for you. All right, so of course, use summation notation and write this using summation notation. And of course, there's a do later. We've already proven Roman numeral 1. Well, go ahead and prove 2 and 3. Be really good practice. These are perfectly fair game test questions. So I recommend that you go ahead and prove those. And you can bring any questions to office hours after you give it a try. Okay. So that's it for section 5.2, where we've proven a bunch, we've proven some statements with summations and products. But now I'd like to shift gears because there's other kinds of statements that are true that require mathematical induction. And in fact, we looked at 3 statements last time just to understand what it means to have a statement concerning an integer n, remember? One was a geometry statement about the sum of the internal angles, the interior angles of a polygon, right? We're now in section 5.3, and it's more proofs by mathematical induction, but now we're going to use a different definition. We want to prove some statements that involve the notion of divides. Why not? It's one of our favorite definitions. So I'm going to restart the numbering here and call this example 1 since we're in a new section. Let's prove the following, that 5 raised to the n minus 1 is divisible by 4 divisible. I need a visit. Divisible. Divisible by 4 for all integers n greater than or equal to 0. So our n naught, folks, of course, is 0. This is the first time that we started at 0. All right, here we go. Let's do it. Proof by mathematical induction or by mysterious intuition. Let P of n be the statement, and I'm just going to rewrite it using divides notation, okay? 4 divides 5 to the n minus 1. Okay, that's our divides notation. I'm comfortable with that. Okay, basis. First sentence of our basis. Let n naught equal. What's n naught going to equal, everybody?
0.
Yep. What do we wish to show?
P of 0 is true.
Yep. Don't close up your thinking brackets yet. We're going to expound on that. I want to look more closely at what that means, i.e., we wish to show that 4 divides 5 to the 0 minus 1. But as usual, anything involving divides, I want to unpack that just a little bit more, i.e., that 5 raised to the 0 minus 1 is equal to 4 times m. You know, it's a multiple of 4. M is in Z. Now I'm ready to close up my square brackets. I anything involving divides, man, I really need to unpack it so I can figure out what I'm supposed to look at. And I know we've discussed this before. If we just leave our wish like this, we wish to show 4 divides, whatever. Just naturally, we read 4 and we think maybe we're going to be trying to look at 4, right? But that's not what we actually need to be looking at. We need to be looking at the 5 to the 0 minus 1, right? That's what we have to show is a multiple of 4. So that's one of the main reasons, and it always has been the reason why I unpack the divides wish, so that I really know what I'm supposed to be looking at. We're supposed to be looking at 5 to the 0 minus 1. So observe. Let's take a look at 5 to the 0 minus 1. What is 5 to the 0 minus 1?
0.
Why?
5 to the 0 is 1. 1
That's
minus
right.
1 is 0.
Good. 5 to the 0 is 1. 1 minus 1 is 0. Now, if we didn't know what our wish was, we might just stop right there. See what I mean? But you see, because we have our wish right in front of us, we realize we have to keep going. We have to show 0 is a multiple of 4. So keep going. 0 is equal to 4 times what integer?
0.
Yeah, 0. You know, and then you simply say, hey, and 0 is an integer. I'm talking about this 0, not that 0, right? That's why I'm underlining it, so you know I'm talking about this 0. Okay, so 4 divides 5 to the 0 minus 1 by the definition of divides. Or divisibility, I think it says in WebAssign, but I hate that. And P of 0 holds. We have just proven P of 0. You can just state that. P of 0 holds. All right, so we can see P of n up here. So when we write our induction step, let K greater than or equal to 0 be an integer. That's always the first sentence of the induction step. Introduce k. Assume P of k is true. That's our inductive hypothesis. Let's expound on that. What does it really mean? Well, assume that 4 divides 5 raised to the k, whole thing minus 1, right? Just replace the n with a k. But I'm not happy with that. I need more. I know to use this hypothesis, I need an equation. Equations are our proof money. So let's write the equation that goes along with the assumption that 4 divides 5 to the k minus 1. That means 5 to the k, whole thing minus 1, is a multiple of 4. Say 4q, where q is in z. You could use m again if you wanted. The m was, it's already done. You could use it again. It doesn't matter. This is our proof money. It's an equation. See, we can do something with this. We can make a substitution once we have this kind of version of 4 divides 5 to the k minus 1. All right, so let's look at our wish. Well, what do we wish to show? We wish. We wish to show. Can everybody write the wish? If this is P of k, we wish to show P of k plus 1, i.e., we wish to show 4 divides 5 raised to the k plus 1 minus 1. But I need an equation, i.e., we wish to show 5 raised to the k plus 1, whole thing minus 1, is equal to 4 times, some integer, I'll say r, where r is in z. That's our wish. So here's my dreamy wish cloud. We're trying to get an equation that shows that 5 raised to the k plus 1, whole thing minus 1, is a multiple of 4. So we know what to look at. We know that we're going to look at 5 to the k plus 1 minus 1. Now this one's kind of fun because somehow we're going to be starting with 5 to the k plus 1 minus 1. And from that, we're going to have to extract a 5 to the k minus 1. So this is quite different from our summation problems. And yet still fun. Here we go. We've got our induction hypothesis up there where we can see it. We've got our wish where we can see it. Observe. Here we go. 5 to the k plus 1 minus 1. It is like having a left-hand side and a right-hand side. We're starting with the left-hand side of this equation and we're working to get the right-hand side, but we don't usually say it because it's not presented as a formula. All right, so what can we do? How can we get a 5 to the k minus 1 when what we see is 5 raised to the k plus 1? Think about it. What does 5 raised to the k plus 1 even mean? It means 5 is being multiplied times itself, k plus 1 times. So we've got k of them. We've got one more than k of them, right? We've got k plus 1 copies of 5 being multiplied together here. So couldn't we just write this as 5 times 5 to the k minus 1? Sure we can. That's exactly what we do. We extract 5 to the k by pulling out one of the 5's. Now, 5 to the k minus 1 is not what we have here. We've got 5 copies of 5 to the k. We only want one copy of 5 to the k. And then we have the minus 1. So again, we have to figure out how to extract one copy of 5 to the k when we got 5 of them sitting here. It's like having 5 cats. We just want one cat. Well, look at what we're trying to do. We're trying to prove that this expression turns into 4 times an integer. This might be a good time to try to introduce a 4 into the mix. Isn't 5 equal to 4 plus 1? Sure. So if we rewrite 5 as 4 plus 1, what it's going to allow us to do is say, oh, okay, when we distribute this 5 to the k across this parentheses, we'll have 4 copies of 5 to the k plus 1 copy of 5 to the k. And that gets us just a plain old 5 to the k, and then minus 1 is still sitting there to use. See that? So why did I do that? Because I was looking at this and realizing that to make this substitution, I needed a 5 to the k minus 1, right? So first we pull out a 5, then we rewrite 5 as 4 plus 1, distribute the 5 to the k back across, and sure enough, here is the left-hand side of the equation that is our induction hypothesis. We can substitute in now for this. Oh, and isn't it convenient that this other term has a 4 being multiplied times it? See, that's kind of the nice thing too. All right, let's make our induction substitution. 5 to the k minus 1. So we've got 4 times 5 to the k plus 4q. This is by induction. We just burned our proof money. And now we're not going to use it again, so I can slide this up. What are we looking for? We're looking to get a 4 extracted out of here. And sure enough, very handy that we have the 4 there in the first term. And of course, the 4 is in the second term by design. And now we simply have to discuss this being an integer. We know how to do that. Oh, y'all do a great job with that. You know, since K and Q or Q and K are in Z, and Z is closed under, I guess exponentiation is just shorthand for multiplication. So under multiplication and addition, it's the usual argument. R equals 5 to the k plus q is in Z. So, in fact, what do we start with? 5 to the k plus 1 whole thing minus 1 is equal to 4r, where r is in Z, which means, of course, that 4 divides 5 to the k plus 1 whole thing minus 1 as desired. So we've just proven P of k plus 1, and now by the PMI, and I want to show you a shorthand, because if you're running out of time on the test, right, you don't have to write the exact statement that you proved. You can just say P of n holds for all n greater than or equal to, and I mean, we know it's an integer, so you could even skip that. Just say for all n greater than or equal to, and I think we started at 0 here. So this is a short way, if you're running out of time, to express that we're going to use the PMI to finish it off. And that, my friends, is day 19 lecture. How many proofs by mathematical induction did we do today? We did one sum, right? We did a summation one. We did a product one. let's see, we did a sum, we did the sum of the evens, and we did the product of 1 minus 1 over I equals 1 over n. And then we did the divides. So we've done 3 proofs by mathematical induction today, plus the proof last time. So that's 4 proofs by mathematical induction that you have seen. And I hope that that should be enough to help you structure your proofs by mathematical induction in the special homework number 9 that's due next Wednesday. Let's go to our gallery view. Every single one of these proofs is a little different because the algebra always requires something a little different, but the structure of these proofs is the same. You know, you always introduce P of n, start your basis step, let your reader know what n naught is, prove P of n naught, start your induction step, state that k is an integer greater than or equal to n naught, and assume P of k. The wish is always the same, prove P of k plus 1 holds. The algebra in the induction step is what is going to be the sticking point for some of you, but it's a puzzle. Just keep your eye on the prize, right? Write what you wish out so you can really see what you're going to start with and what you're trying to get. Then you have a much better chance of getting there. Proofs by mathematical induction are like magic. So listen, if you're in the tune section, just shoot me an email and just tell me one of 4 choices. Friday morning, Friday afternoon, Monday morning, Monday afternoon for the final. If you're at TU, the final is already set in stone. It's in the afternoon on Saturday, and I will get you the room number. I think it's 3 to 5 and the time, in the next week or so. Tune people will have to find a room. Somebody will get us a room, and I'll know what it is in plenty of time. But I don't know what that is yet until we know what day we want to do it. So
What
there's
is
3. Go ahead.
what is your definition of afternoon? I work in the schools. I'm at work till 4.
You
What's
don't
your
get off
definition
work
of
till 4.
afternoon? Yeah.
Yeah, yeah.
I
I
can do
think the
both. It's
tune,
fine.
right? Yeah. Afternoon would be like 1 to 5.
Okay.
So you may have to get somebody to cover for you. Like we could do a late afternoon, like a 3 to 5 on Friday or Monday.
I'll take off. We're good.
Take a day off and study up in the morning. Yeah, I'm kind of partial to an afternoon one. So let me know. Look at your other schedule, look at your other final exams. All right. All right. Well, I'm going to stop recording unless anybody has a question that you would like to have recorded. All right. I'll stop recording.